Hi, my name is Shafak. I'm a testing specialist with a dedicated focus on automotive and heavy equipment testing. Today, I'm going to present you our model-based system testing for durability specifically in the context of virtual sensors. I would just like to start with a nice expression that I really like from Albert Einstein. So it basically says like in theory and practice are the same. In practice, they are not. With this one, I'm actually referring to the vehicle development activities in the context of simulation and testing. So we see more and more people prefer to have simulation-based validation methods instead of physical testing, because there is the simple fact behind physical testing takes quite a lot of time and it also costs you a lot of money. So which means that simulation can easily represent validation or not, because it's not always very straightforward that simulation results are not the same as the testing results, let's say. So I will try to open two different windows for the same scene, let's say. The first window will be about the simulation part, where I will be presenting our Simcenter AMISIM solution in the context of system simulation. Let's see how it looks like. So here we have the Simcenter AMISIM. Actually, AMISIM is really a powerful platform for the system simulation. So you can model your components, your vehicle, your structure, let's say, in terms of mechanical components, electrical components, and so on. So in this particular example we see on the screen, we have, for instance, a kind of car model with the wheels, with the suspension, with the upper body, stuff like that. So what you can do, you can easily apply a force on the wheel center, let's say, as a representation of the wheel forces coming from the road to your wheel center, let's say. Then you can use AMISIM to cascade these loads to certain components on your structure. You can cascade it to the suspension just above this wheel, or you can even go even higher, let's say, to the body components that you can cascade the loads, which you think, maybe you think you have some critical components on the body or the suspension, so you can easily rely on these cascaded loads, let's say. But there are some challenges or difficulties, let's say, in terms of using only the system level simulation as a kind of a validation method on the product development cycle. So these would be like, okay, so we can easily put like a generic loading on the wheel center in this particular example, but can we make sure that this is the realistic loading? Because again, we are putting only a kind of generic loading. At the same time, it should be also quite crucial, let's say, because we need to see that the model should be also validated and accurate enough in order to see like this loading on the wheel center will be cascaded to the upper components correctly, let's say. So these are the main challenges when we use only the system level simulation. Now I'm opening the other window, which will be about physical testing, where I will be showing you our Simcenter SCADA's hardware, data acquisition hardware, and Simcenter Testlab software, let's say. So here we see a kind of electric car that we just took and went to some kind of a proving ground in order to acquire some physical loads. So the car you see on the screen, it was actually instrumented with many different sensors, like wheel forces, as you see on each of the wheel, let's say. So we put a lot of strain gauges all around the car. We put a lot of accelerometers. We put a lot of displacement sensors in order to understand the operational conditions which are affecting my car completely, let's say. So, but there are also some difficulties and some challenges also present in this picture as well. So first of all, do we have enough sensors? So this is really taking us to think about the resources that we have actually. Another important challenge will be, even if we have enough number of sensors, do we have enough time and manpower for the instrumentation? Because again, for durability, we are mostly taking into account of long measurements, long durations, let's say. So which will cause us a lot of effort, a lot of manpower that we will need during the instrumentation. Because also, again, as I mentioned, we put a lot of sensors on a car when we consider durability testing. So which means that the instrumentation will also take quite some effort, let's say. And also, last but not least, are all sensors locations accessible? Because it's possible that some components will be hidden behind some of the other components, and these hidden components, sometimes we also need to put some sensors on that, like strain gauges, accelerometers, and so on. So it will be quite efforting, let's say time consuming to reach that hidden components. You need to take off some components, instrument the parts that you want to instrument, then put the other parts back again. So it will be quite time consuming. So the question I have in mind, I like to ask questions, by the way, as you see, there are many questions over here. So can we use simulation to reduce the instrumentation effort? Let's say, can we use these two platforms, these two windows, simulation and testing, with a combined setup, let's say, in order to reduce all the effort that we spend actually? Here now we actually see the storyline that I will present today. It is again in the context of model-based system testing with a dedicated focus on virtual sensors, let's say. There are some different issues and limitations that I mentioned in the beginning. Like for instance, in my particular example that I also showed you the car, when we went to the proving ground, we had some issues actually. The first thing that I can mention over here was like the limited number of sensors I had as resource for this real-life measurement. And also, what I will do, I will also come to that point later on. I needed to measure the forces acting on my shock absorbers, let's say. But it was quite difficult for me because if I put a kind of a dedicated force cell on the shock absorber, I can easily change the structure or let's say the behavior of my component. So what I was planning to do is that I just decided to make some virtual sensors which will be representing the forces that I need on the shock absorber, because that's going to be the input for my later phases, let's say test benches that I was planning to do on the laboratory conditions. Then the third thing I can also mention here, it will be the validation of the simulation model. It will be also mandatory for me that I will further use my model for other purposes as well. Here we see, as I said, in the right side pictures, we have the wheel force data, wheel force transducers that I put over the wheels, let's say, and also the shock absorber displacements. So the displacement was easy for me. I could easily put a kind of a swing pot, for instance. Then I can easily see how my structure behaves actually under tough conditions. So what I did basically is that I use Simcenter SCADA's hardware, as you see on the left side picture. So I instrumented the car with many different sensors and connected all those sensors directly to my hardware. Then what I did is that I used Simcenter Testlab software in order to do channel parameterization for each of these different sensors, let's say. Because all of these sensors, they have different conditioning environment. I need to put a kind of a correct sensitivity for each sensor, correct range, supply, and so on and so forth. So these will be done actually on the Simcenter Testlab software environment. Then again, I use exactly the same software, Simcenter Testlab, in order to classify these loads that I acquired from the real-life conditions. Because I also need to do some analysis based on some durability fundamentals. It will be also important for the further steps, let's say. So in parallel, what I also did is that I use Simcenter MBST in order to create a model which represents the full suspension of my car. We see on the below picture, so this is actually representing a spring mass damper system, a basic one, that I put the forces, the wheel forces coming to the wheel from the below part, bottom part, let's say. Then this will goes directly to the suspension components, then it will also reach to the body level, let's say. So it's a kind of a very basic setup that I did on the MBST. What is also important to mention here is that most of the simulation platform, they have the enability to output their models via .fmu platform. It's a .fmu data file. It's a kind of a platform in order to enable data exchangeability, let's say, across different simulation platforms. So what I will do, that's the fun part. So I can use this .fmu file that I created directly from the MBST, that I can also use this and import it into my testing software, the same software that I'd used for channel configuration or further durability load data analysis, let's say. So what I will do after importing this model, I can compare my simulated results with my physical testing results, let's say. What I can even further do is that I can check my, let's say, model parameters like spring, let's say, rate, damper rate, or the stiffness rate, this kind of things that I can already check. And I can even further tune these parameters directly from the testing software without a need to open the MSIM again to do all this and again make a kind of an output of .fmu file. It's not the case. I can easily do everything directly in the testing software. This then will also allow me to extend my real-life measurement with accurate virtual sensor, let's say. Okay, so I just made 5 different chapters in order to achieve my goal. In order to, again, as I said, my goal will be extending my real-life measurement with some accurate virtual sensors. In this case, I was really referring to shock absorber forces that I couldn't physically measure. So these will be on the left side. We see the steps that I will follow in this presentation, let's say. So firstly, we will start with understanding, let's say, analyzing the test loads, because I'm going to also show you that I have 2 different surfaces in the proving ground that I could measure the data on. But it was a very vital for me to understand the worst case scenario, to see which one was most damaging for me. So I will show you all those. Then we will see how we can easily import MSIM models via .fmu file into testing software, Simcenter Testlab. Then we will also see how we can put the real-life loads, wheel forces in that case, as an input to my MSIM model directly in testing software. Then I can also see how I can, let's say, further give results on the simulation platform indirectly, let's say, testing software. Then the third chapter, we will be talking about verification of the model accuracy, let's say. In this particular example, we will compare simulated results with testing results in order to see how verified my model is. Then, as fourth chapter, we will go into the correlation of the model chapter, which is actually about further tuning your model parameters based on the results that you get with the previous chapter. And as final step, we will try to extend our real measured data set with some accurate, or let's say correlated virtual sensors. That's going to be the goal of this presentation. So let's already start with the first chapter. Again, it will be about analyzing the test loads. As I mentioned, in the proving ground, we have 2 different tough conditions, let's say. The first one you see on the left side picture, it is from a Belgian block road surface. The second one on the right side, it's from a sawtooth surface. This has actually different characteristics, and the loading which affecting your components, your vehicle, will be different in these different environments, let's say. So I will try to see which one will be most damaging for me that I can further use on my further processes, let's say. By just taking into look of, let's say, the time data that I could acquire from these different surfaces, it will be quite hard to say, to answer this question. So I need to go into the damage domain rather than the time domain. So here is the setup that I did on some, let's say, different components. So we see wheel forces that I could measure from each wheel. Then I also put on the second picture, we see some DC accelerometers that I could put on the wheel hub side. Then I also put some, again, DC accelerometers on the body side at the upper level, just after the suspension, in order to see the effects of the suspension on the body. And also the last picture on the right side, we see some displacement sensors, some string pot, let's say, I put in order to understand the relative displacement of my shock absorber, let's say. Now I will try to demonstrate this by using our software, Simcenter Testlab. Directly from there, we will see how we can analyze these test loads. So I will switch from presentation mode, then I will open the software, Simcenter Testlab. Okay, here we see the interface of Simcenter Testlab. That's the platform for us to use any type of testing, for any type of testing purposes, let's say. We can use it for channel parameterization. We can also use it for detailed durability analysis. So now I actually try to use the second thing that I will try to demonstrate to you how you can easily analyze your testing loads. So on the left side of the picture, that I will also move my mouse over there, you see there is a chapter, let's say section called pre-processing. There I actually have 2 different run actually that I could acquire from 2 different surfaces that I also introduced before. So Belgian block and sawtooth. So I click on my section, As you see on my pivot table, that's a kind of a very nice Testlab feature, by the way. We adapted the pivot table into the software. So whatever you click from the pivot table with a preview functionality, you can easily see the signal in, let's say, in detail. So as we see on the pivot table, there are already some classification that I did. As you see, there are 8 different channels over here. And there are some DOF IDs which represents these channel IDs. The function class, all of them are time-based data that we acquired. And these columns we see on top, these are from Belgian block and Sawtooth. So 8 channels from Belgian block run and 8 channels from Sawtooth run. So I'm just using the preview functionality right now. I'm clicking on one of the signal over there. So it's for the front right spindle forces that I could measure by using the wheel force transducer. So I also did the same thing from Sawtooth. As you see, the unit was, you see over the picture, the histogram, let's say, it says the unit is Newton actually. So it's a force channel, and I could measure it with a relatively small duration, let's say only up to 14 seconds. What I can further do, I can further compare these 2 runs. I mean, for the same channel from 2 different runs, Belgian block and Sawtooth. We can easily have an idea saying like, okay, the Belgian block, which is the red curve you see over here, it has higher peaks, higher amplitude ranges, which can most probably give me the more damaging scenario. But in order to be on the safe side, we need to do some durability analysis in these 2 different runs, let's say. What I can do furthermore, I can click on my pivot table 8, as you see for Sawtooth. I can easily see all of the channels that I could measure under this run. So the channels with the unit Newton, millimeter, so displacement channels, and the acceleration channels over there. If I click on 16, then I will have access to all of them. I mean 8 channels from Belgian block and 8 channels from Sawtooth. So I right click on from the pivot table, as you see, I put all of this into my input basket. Then I'm going to switch my layout in order to show you the predefined process that I set. So by using the graphical interface of Testlab, I just made a kind of a processing in advance, let's say. So as you see, 16 different channels, 8 from Belgian block, 8 from Sawtooth, coming to this block, the input block. Then I split the force channels, so wheel force transducer channels over here. So this flow will go in that way. Then I will calculate some rainflow counting. As you see on the right side, under properties pane, we have some parameters that I can easily change. So these are user definable parameters. I will leave them as it is for now. So default parameters will be fine in this particular example. Then over rainflow, we calculate range pair cumulative cycle. Pseudo damage, that's also important, which will give us an idea about the damage comparison, let's say by the end. So as you see from the properties pane, I can select the damage method. In this case, I selected stress life. And under the ascent curve, there is a very nice library that we adapted in Simcenter Testlab. So you can check all of these different ascent curves. As you see, we can change it actually. If you are not satisfied with this library, you can already create your own ascent curve by changing the curve type, maybe to Euler. You can identify an R ratio. You can change the endurance limit, the cave slopes that you can already change it. But again, I will proceed with the default settings. Then the range pair versus damage will also give me some idea about the comparison of the different kind of loads. This, by the way, this rainflow type of analysis will already help you quite a lot in order to classify your loads by amplitude ranges and the repetition of these amplitude ranges, let's say. So we will further see when I will be showing you the results. Then another flow goes here to the acceleration channels. So I split the acceleration channels. Then I calculate PSD, power spectral density. As you see from the properties pane, I can change the spectrum resolution, number of lines that I selected, and the window type. So I proceed, I already identified this in advance, so I will not change it. Then another flow on my process will go to here, as you see, this flow. So displacement channels will be split from the whole measurement. And then I will calculate again rainflow counting, now level crossing, and also time at level in order to further classify this displacement, let's say, displacement channels. So I'm going to push run. Then I will change my layout in order to have a better view on the results. So the process has already been executed quite shortly, let's say. Now I'm going to see my active section, which is analyze test loads, as you also see here as hidden under shadows, which means that active section means that whatever you process, the results will be saved under that specific section. As we see now on the pivot table, there are some different things that we see actually. So there are the channels that we were talking about, the 8 different channels, the Belgian block and sawtooth run, and these are the function class, which means that these are the results of my processing blocks that I set, like rainflow counting, pseudo damage, time at level, level crossing, and MBST. So I'm going to show you the results one by one. First of all, from channel number 13, which was front right spindle forces. I'm clicking on the rainflow results from the Belgian block, which already gives me some idea about the content of the load, let's say. So here we see the zero range diagonal, and most of the cycles are spread over this zero range diagonal, let's say, which means that these cycles have more repetition but less damage contribution, let's say. But we also see some cycles, let's say amplitude ranges a little bit far from this zero range diagonal, which means that these are more damaging loads but with less repetition, let's say. I can quickly check the same channel with the rainflow results again on sawtooth. As you see, this one is quite different than the previous one. We see again zero range diagonal, which is quite obvious, but we also see some more damaging cycles, and in between I almost have nothing actually, which means that I have, in this particular loading scenario, I have very damaging cycles, and with a really small, with the cycles with less damage contribution, let's say. So in order to compare these two, I'm going to show you range pair results together with live statistics, which is the result of pseudo damage. Now we see the red curve, which is Belgian block. As expected, we see higher amplitude ranges compared to sawtooth. And also this is, by the way, the force amplitude ranges versus cumulative cycle. And below we have the force amplitude ranges and cumulative damage. As you see, the red one, Belgian block, is much more damaging compared to sawtooth. And we also see this from the pseudo damage calculation, as you see over here. I'm comparing the same thing on the rear side of the car. Let's see if it's also the same. As expected again, from the range pair results, we have a more, let's say the amplitude ranges are higher compared to sawtooth in Belgian block. So the pseudo damage is even, the difference is even higher if you check the rear side of the car. We can also check the level crossing results of the displacement channels. Again, the red one is Belgian block, which means that our suspension is giving us more relative displacement on Belgian block compared to sawtooth. But I'm going to show you something different, like for instance on the acceleration signals where we calculated the PST. As you see, the red one is again, the red curve is Belgian block, so we see more energy content on these vibration channels, but it also shows me some frequency content. By the way, this PST is based on frequency, as you see hertz on the horizontal diagram, horizontal axis over here. So, which means that in this particular frequency content, we see higher amplitudes on sawtooth, which means that you need to be very careful. Okay, Belgian block is more damaging, but for those specific accelerometers on the vibration content, I might see some resonance effects on some certain frequencies. I'm going to show you something very nice, that I will put a kind of harmonic cursor, that I can easily set this, and I will immediately see that at 75 Hz, I have a very high peak on sawtooth, as you see, which is much higher than the Belgian block. And on the multiple harmonics of 75 Hz, I see the same effect. So which means that I need to be very careful when I use these channels because on the vibration content for the selected sensors, I can see more damaging content for certain frequencies, let's say. So that's going to be my process. I'm going to remove this and accept my results. And everything I did under processing is now saved under this active section. So now I'm going back to my presentation. Okay, this is where we left. So what I did, I compared different signals from different rounds, sawtooth and Belgian block. I could easily demonstrate it like, okay, Belgian block is more damaging for me, and Simcenter Testlab software as an operational benefit gave me the enability to have easy access to engineering insight in the data. It's a little bit further, much further than comparing the time data, let's say. So, the second chapter. Now it will be a good idea to proceed with the second chapter, where we will be importing the AMSIM models into the testing software, Simcenter Testlab, and we will apply real loading as an input to this simulation model. Let's now demonstrate this in the testing software, which is again Simcenter Testlab. So I'm going to quit from presentation mode. Then I will also bring my software back again. So it's here. From the previous section, you might recall that I had 16 different channels on my input basket, but I just decided to proceed with only Belgian block because I already identified like, okay, Belgian block is more damaging for me. So it's not necessary for me from now on to use the sawtooth. So what I will do, I will click on only the Belgian block run and replace, sorry, I need to go to my pre-processing again where I stored all my runs. So Belgian block is over here. I will right click and replace an input basket. So which means that all the rest are now removed. So I only have Belgian block as an input to my further process. So I'm going to my processing environment back again. Let's say create process layout. So now we see the inputs, the Belgian block will come here on this block. Then I will split only the wheel force transducer channels because this wheel force transducer channels will be the input for my model, the AMSIM based model, let's say. Then there is a special block that we have in Simcenter Testlab, which is called FMU. So by using this block, I will import my AMSIM model into the testing software. I'm going to show you how. So here is the path on the right side under properties pane. I see FMU path, where I already linked my FMU file that I exported from AMSIM. Then there is also input over here. I'm clicking on that one. So you see the wheel force transducer channels for the right side of the car. This one is only for the right side of the car. So I have front and rear suspension. So I have channel 13 and channel 33 as input, and these are the units and quantities that I already set. Now I'm going to the outputs. These are actually the outputs that I was planning to take from the AMSIM model. So there are some, the first 6 channels are the same as measured ones, exactly the same. Just will give me an idea to compare this simulated and the measured runs, let's say. But the channel 14 and 34 are something new actually. The 14 is front right shock absorber force that I couldn't measure, and 34 is rear shock absorber force on the Z direction that I couldn't measure. So I click on that, and there are also some possibilities. If I click on parameters, I can also easily see which parameters that I already selected on the AMSIM environment. So I will not change any of the parameters for now because I just would like to compare these 2 runs later on. Then I will see how I can further tune these parameters. So as you see, there are some possibilities for spring rate, damping ratio, let's say a lot of different coefficients that I can already select, but I will proceed with these default parameters that I set from AMSIM environment. Well, I'm going to show you one more thing from AMSIM environment that I already opened. So this was the model. This is, by the way, the interface of Simcenter AMSIM. This is the model that I created on AMSIM software. So as we see, it's a kind of a simple mass spring damper system. I apply my forces over here, the wheel forces. Then there is the mass for the wheel itself. Then the suspension, the mass of the suspension, and the body itself. In between different components, I have already identified some sensors like force sensors and acceleration sensors in order to get results in between these components, let's say. And then what I can easily do, I can go to my interfaces and export this via FMU. And this exported FMU is already being used by me in the Simcenter software, Testlab software that I was already showing you. I'm going back to the Simcenter Testlab. So FMU from AMSIM is already here. Then I create, after the FMU, I already create a kind of block which gives me the suffix. Let me show you. It will add a suffix of virtual to my run in order to give a better representation when I compare it with the measured one. And then unprocessed one, or let's say the channels which are not really processed, also goes to this flow. So I also put a suffix of measured in order to give me a better understanding when I compare these two. I click on run. Then I go to view data layout in order to show you the results. Everything now will be saved under this section to apply loads to model, which is this one actually. Now everything will come here one by one. Now we see the results. So I had before 8 different channels on the Belgian block. Now I have 10 because I have 2 additions, channel number 14 and 34, which are shock absorber forces that I really need. As you see from the columns, upper columns, Belgian block measured 8 channels over here, and I didn't have channel 14 and 34 over there. But in Belgian block virtual one, now I have channel number 14 and 34 as you see over here. So these are my shock absorber forces that I could simulate it. But it should be quite important actually to compare the channels which I could measure with the ones that I could simulate it as well. Like shock absorber displacement, which will already give me quite some good idea. So this is the measured one and this is the virtual one. I overlay them together. As you see, these are quite comparable, which is nice actually. If I go a little bit deeper, I see like, okay, the amplitudes are similar. This is, by the way, front right shock absorber displacement signals. So I see them quite comparable. This one is the measured one and the green one is the virtual one. But there are some differences, as you see over here, over there, and there are some differences, I would say. In order to understand if my model is accurate enough, I need to further process this data with some durability fundamentals. That will be the subject of the next chapter, let's say. Now I will just go back to the full mode, let's say, on the signal, and I will accept my results. Then I will open my presentation again. So what I did with this process is that I could easily simulate the real life loads. I mean, simulated the loads with the real life measurements, let's say. I imported the AMSIM model into my testing software, and I could easily compare this measured and the virtual runs by taking into account of different nice fundamentals on the Simcenter Testlab. But what I will do furthermore, I will try to compare simulation and test by using some innovative load data analysis, durability load data analysis. So this will already give me an idea about the accuracy of the model, let's say. Let's again demonstrate this on the software. So I will again quit from the presentation mode. Then I will open my software again. So what I will do here is that, let me come to here. So I will use the previous section, the results from the previous section, let's say, the measured run and the virtual run. I'm going to put this into my input basket. So which means that in my input basket, now I have 2 runs, as you see over here. In total, I have 16 different channels. So I'm going to show you the process that I said over here. So all the runs will come here. I will only take the shock absorber displacement channels because these were the channels actually I could measure and simulate it. So it will already give me an idea about the accuracy of the model, let's say. Then I will calculate rainflow counting over these displacement channels, again in order to classify them based on the amplitude ranges and the repetition, let's say. Then another flow will go over there in order to calculate the PST in between these different channels, displacement channels, let's say. Then over rainflow, I will calculate the same as I did before, range pair, pseudo damage, and range pair versus damage. So let's run the process now. Now I'm going to view data layout again, while the process is already running. So now it's already executed. So everything is now stored under this active section. Number 3, verify model accuracy. Now we see only 2 channels because I had only 2 displacement channels. One from the front right direction side of the car, and the other one is from the rear right side of the car. So we see again the DOF ID is over here, and these are the processing that I set on my flow, let's say. Okay, let's compare them. So first of all, I will put again like I did before, range pair and live statistics. So I'm now checking the front right side of the car. So as we see, we have quite comparable results on the shock absorber displacement. This is, by the way, amplitude ranges versus cumulative cycle. It's quite similar. And also, if we check the amplitude range versus cumulative damage, it's again very good, I would say, a little bit less than 95% that I have the correlation. and you see the pseudo-damage values are also quite close to each other. So which means that, by the way, let me quickly say the green one is the virtual one. So the virtual one is a little bit more damaging compared to the measured one. Let's check the rear side of the car. If we have the same, let's say, accuracy level, but unfortunately, as you see, especially from this range pair, the second one, range pair versus the damage, as you see, the green one is my virtual one and the red one is my real one. So I'm giving almost 2 times more damage by taking into the account of this model that I created on MSIM. So for rear side, I have quite some issues, which means that I need to further tune that. The basic thing that I could easily think like, okay, if I give more damage, especially for the rear side, which means that the damping characteristic should be a little bit more than I said in the beginning, let's say. So I can easily further tune that actually. If we also check the pseudo damage results, as we see over here, as I said before, it's close to, let's say, 2 times more damage. Let's say if we check the measured versus the virtual one will be giving a lot of damage compared to the measured one. So I'm going to accept the results for now, and for the next chapter, I will try to further tune the parameters on the model in order to, let's say, increase the realism on the model accuracy, let's say. I'm going to accept the results for now. Then I will go back to the presentation. Okay, this was where we left. So what we did actually, we took, again, we already imported the MSIM model into the Testlab. In this specific chapter, we compared simulation and test. Then the benefit that we can get by using Simcenter Testlab for such purposes will be about assessing the model quality in a systematic way. So you can save your process and you can always use the same process with some fine-tuning, let's say, depending on your application. This will already give you a kind of a standardized way in order to assess your model quality. So the next chapter will be about model correlation. So in this chapter, we will see how we can increase the model fidelity by tuning the model parameters. Let's see how we can do this in the software, let's say. So I'm gonna again quit from the presentation mode and open the software back again. So, as you might recall from the previous chapter, we already put the required runs that we want to use actually. So I will not change my input basket, which means that I will be using my measured run and the virtual one as an input to my new process, let's say. So I'm going to go to create process layout. Now there is a kind of an advanced process that we see over here. So I'm going to introduce you to the process itself. So Belgian block measured and Belgian block virtual ones are coming here to my input block. Then I split the run with the suffix of measured. So I'm only taking the measured one, let's say. Then I split only the wheel force transducer channels because I will again create another virtual run with optimized parameters, let's say. So for that one, I will be using this new FMU block, as you see over here. The FMU path is still the same. The inputs are exactly the same as before, channel 13 and 33, wheel force channels as input. The outputs are also the same, nothing changed over here. I have again channel 14 and 34, shock absorber force channels as an addition to my measured signals, let's say. But there are some changes that I already did here. So as I told you before on the previous chapter, the damping ratio was a little bit tricky, let's say. I need to further tune the damping characteristic of the system, let's say. What I did here is that, as you might recall, on the front suspension, I also have I might need some correlation maybe, but basically I need more correlation on the rear side of the car. So the last 2 parameters you see over here, these are the spring rates, by the way. So what I did actually, for the front one, I took it from 20,000 Newton divided by meter up to 25,000. And for the rear side of the car, I took it from 25 to 46K. So I changed it quite significantly, let's say. So let's go back to my process flow. Then this measure run will also come here. I put another naming on this one. I put identify as Belgian block real. And then the measured run comes here and the virtual run also comes here. Then I put a naming of virtual run. This is the initial virtual run that I created without any parameter optimization on the model. then each of these three runs, the virtual optimized, the real one, and the virtual initial one will come here, where I will split this displacement channel, because again I will take into account of displacement channels, because displacement channels were the ones that I could measure and simulated. Then after this simulation, the splitting of displacement channel, I will calculate again PST, rainflow counting, and over rainflow some range pair calculation together with the pseudo damage calculation. So I'm going to run this process. At the same time, I will be switching my layout to view data layout in order to show you the results in a better way, let's say. So my active section was number 4, correlate model. So everything will be saved under this section actually, which will come up, yes. So what I will do, I will firstly filter only channel number 139 and 141. So these are the displacement channels that I need. As you see, and these are the processes that I set on my processing flow. And the vertical columns, as you see, these are actually the ones that I identified as new runs. So Belgian block optimized. This is the optimized virtual run, the first one. The second one is the real one. And the third one will be the virtual initial run, which means that it's the one that I didn't do any optimization on the parameters. So what I will do, I will check live statistics. This is, by the way, for the front suspension, together with range pair cycle and range pair damage. Let's first check the range pair cumulative damage, the middle one. Now we see the blue one. This is again for the front suspension. Now we see the blue one is the virtual. This is without the optimization. As you see, it's further compared to a real one and also the virtual optimized one. These two, red and the green one, these are actually real one and the virtual optimized one. It's quite closer to each other. If we check the pseudo damage, it will already give me the same opinion actually. As you see, virtual run without optimization, it's much more, giving much more damage compared to the real one and the virtual optimized one. Let's check this. This means that I already correlated my front suspension. Let's see if it's also the case for the rear suspension. I will check the rear suspension now. Again, the same comparisons that I will do. As you see, this is maybe the middle diagram will already give us a lot of information as did before. So the blue one is the virtual one without any parameter optimization. As you see, it's much more damaging compared to real condition. So the real condition was back again. The green one was the real one. And the red one is the virtually optimized one. If we also check the pseudo damage comparison, pseudo damage values, the bottom one is the virtual one without optimization. It's much more compared to the real life condition, which is the middle one. And we see the virtually optimized one, which is quite close to my real one, which means that I have correlated with this parameter optimization. Now I correlated my model, and I also see this directly from my shock absorber displacement channels. Now what I can do furthermore, I will now use this optimized model in order to output the shock absorber forces that I was looking for. Then I will combine these shock absorber forces with my Belgian block real measured signals, let's say. That's going to be the subject of the next chapter. Let's now accept the results first, which means that everything will be saved under section 4. Now I will go back to my presentation. So what we did actually with this chapter, we increased the model fidelity by tuning the model parameters. And what is the real benefit, the operational benefit behind is that we increased actually model prediction accuracy. So let's go to the last chapter, which will be about extending the data set. So what we will try to do is that we will try to virtually extend the test campaign. As I said before, we will add the shock absorber forces from the virtually optimized run, and we will combine it with the real Belgian block measurement that we could take actually. Let me already show you how I can do this on the software directly. So I'm gonna again quit from the presentation mode. I will bring my software back again. So remember on the last chapter, chapter number 4, when we did the correlation on the model, we created 3 different runs. The optimized one, the virtual optimized, the real one, and the virtual initial one. So I'm going to put them all into my input basket that I will further process. So in my input basket now, I have 3 runs, as you see over here. I'm going to show you the process that I set as a predefined process now. So what I will do, first of all all three runs will come here to my input block. Then I will split only the real one, which is the measured one, will come here, and then other block over here, which is the pass block, which means that only the optimized run, virtually optimized run will come here, will pass here. Then I will select only channel number 14 and 34 out of that. So these were the shock absorber forces which are not available in the measured run. So I will combine these two actually. And then I will put a new naming of run name of Belgian block extended, let's say. So I'm gonna push run. Then I will also go to my view data layout. Now everything is already processed. Now I'm clicking on the section, my active section. As you see, I have only one run over here right now, Belgian block extended, and I have 10 channels instead of 8. Now I have 10 channels because I have extra channels as channel number 14 and 34. These are the shock absorber forces from front side of the car and the rear side of the car. So in total, I have now 10 channels, which is my augmented run, let's say. Okay, now I will go back to the presentation. Let me first, before I forget, accept the results, which means that everything will be saved under my project. Now I'm going to the presentation. Okay, let me see where we left. So what we did actually, we virtually extended this test campaign. And what is the operational benefit behind? So you can easily expand your everyday data set with some accurate virtual sensors. That's the real benefit for you actually. Let me summarize all those in under 5 different chapters. So we started with analyzing the test loads. We identified the most damaging testing condition for us. The Simcenter Testlab software already gave us the inability to have easy access to engineering insight by using some durability analysis methods. Then we used, under chapter number 2, applying loads to model, we just imported the MSIM system simulation model into the testing software, and we applied the forces, wheel forces, as an input to my simulation model. And under chapter number 3, we verified the model accuracy by comparing simulated results with the test results, let's say. So the benefit we take from this will be again assessing the model quality in a systematic way. And number 4, the correlate model. So we increased the model prediction accuracy by changing some parameters on the model, let's say, by taking into account of the comparison results coming from the chapter number 3. And as final chapter, we extended the dataset, our everyday dataset, with some accurate virtual sensors. So here we have our winning combination: Simcenter Testlab, Simcenter Scalas, and Simcenter AMISIM. So 1 plus 1 will not always give us 2, let's say. So the simulation and test will already give us the better models, more insights, optimized testing, as I demonstrated today. So thank you for listening to me. I hope you enjoyed this presentation.